Okay, so you might recall that previously when we were solving equations using logs, I made mention of the fact that if you're using a scientific calculator, your calculator can only handle logs with a base 10 or logs with a base of e. And today what I want to do is introduce the number e and the idea of exponentials with a base of e and logs with a base of e. There's lots of reasons why exponentials and logs with a base of e are common, and exponential functions with a base of e tend to, and logs with a base of e, tend to most accurately represent a number of naturally occurring phenomena. Okay, so it is a nice base to use for exponentials. Next year, next semester, we'll look at the idea of differentiation, but it won't be till year 12 that we combine differentiation with exponential and log functions. But we only know how to differentiate exponentials with a base of e and logs with a base of e. Well, we can extend that into differentiating exponentials and logs with other bases, but the easiest function to differentiate is one with a base of e. And so in some ways, for that reason, we like to use the log with a base of e wherever possible. Now, e, like pi, is a naturally occurring irrational number, and it comes out of a number of different applications. The most straightforward of which to understand is a financial application. I might try and link a video at this point in the recording, not a video by me, but I'll link to another video which gives you an explanation for where E comes from. But there are a number of different definitions, and technically they're written here. E is often referred to as Euler's number, although I believe that it is actually an erroneous attribution, and there's an article on that I've linked on our Canvas page, which talks about the fact that E is no more Euler's number than anyone else's. So an interesting attribution that doesn't seem to be correct. So there are a number of really technical mathematical definitions. Okay, the first one here is actually the financial application explanation, and if you have a look at the article, it talks through that, and I'll link to a video which explains that application, because that's the most relevant one for you to be able to follow. The other explanations for E require all sorts of notations and maths that you're not familiar with, as does this one with this limit. We'll talk about those next semester. But there are lots of ways to obtain the number E exactly. For now, I don't want to really go into that because, as I said, it involves a lot of maths that you don't understand. I'll link to the simplest possible explanation here. However, we really just want to be able to understand this idea that there is another number, like pi, which is an irrational number, so that means that its decimal goes on and on forever without repeat or pattern, and so therefore the only exact way to represent the number e is to call it e. Okay, now e is about 2.718. So a bit less than 3 is a good way to be able to think about it when you're trying to enumerate expressions involving e, and to think about, well, roughly how big is that? If you think about it being just a bit less than 3, that can help you. So when you're using e with your CAS, it's really important that you understand how to do that. Okay, so it's not just about using the letter E down the bottom in the keypad. Okay, so when I type letter E and press enter or control enter, it just tells me it's E. And you'll notice that it was just a normal font E. What you want to make sure is if you are trying to access the number E, E should be being shown in bold, okay, to indicate that it's referring to the number 2.718. Okay, there are specific buttons for E. So over here on the left with your powers, you've got 10 to the power of x and you've got e to the power of x. So you need to, if you want to get the number E, you need to use this e to the power of x button. Now you can then either press delete to get rid of the power, or you could have just made it to a power of 1 and press control enter to see that, okay, that's actually E. And you see the difference between the font, that you're getting that bold font. When you use a log with a base of E, you can do two things. So you can do control 10 to the x like we've been doing, log, and then you want to put E in there, but you need it to be special E. So you're going to press the E to the x button, and then you can press delete to get rid of that power. So you can do it that way. But actually, and I'll talk about this a bit further on in the notes, the logarithm with a base of E is called the natural logarithm, and there's a special button specifically for that, which is when we press control E to the x, we get this ln, which is shorthand for the natural log, that is log base E. Okay, so we would expect if you put log base e of, if you put log base e of e, we should get 1. Okay. All right, so the exponential function, the king of all exponential functions, is the exponential function with a base of e. And as I said, the reason for our preference for e is to do with calculus and differentiation and gradient. Also, exponential functions with a base of e occur widely in nature. Often, growth and decay problems are best modelled with an exponential function with a base of e. But equally, we can always use any base to model an exponential growth problem. Yeah, as I said, it also has a unique property in that its derivative or gradient function is also e to the x, and that's why that's often why we choose to use e to the power of x. Okay, so if we think about sketching e to the power of x, it's just a general exponential function. So same idea. Remember, it's just a base of something a bit less than 3. So we're going to get our same exponential shape. We know it's going to go through the point 0, 1, because when x equals 0, e to the 0 is 1. Anything to the 0 is 1. We know it's going to go through the point 1e. When x equals 1, y equals e. We know it's going to go through the point negative 1, 1 on e. We might write that as e to the negative 1. Same thing. Okay. Or 1 on e. Doesn't matter. And we know the asymptote will be the x-axis. Okay. So y equals 0 will be our asymptote. So it's exactly the same. It just means that your points will have e in them when you calculate intercepts or certain points on the graph. Okay, so let's think about the natural log function. So the natural log function is log to the base e. And alternative notation is ln, as we saw with the cas. I want to be clear about the fact that that's not just cas notation. It is perfectly acceptable to write ln on the paper in place of log base e. Personally, I tend to write log base e. I find it helps me when I'm trying to rearrange the expressions to understand that it's log with a base of e. But you might say, for example, if you're labeling an x-intercept and it's log base e of something, it might be neater and easier to write the shorthand of ln of whatever it is. The natural log function and the exponential function, so the exponential function with a base of e, are obviously inverse functions. If e to the power of x is the original function, then its inverse is log base e of x, or ln of x. And so therefore we can use that property to help us sketch the graph. So if this is our e to the power of x graph here, swapping all the x and y values to get our log base e graph here. So the asymptote will be vertical at x equals 0. The x-intercept will be at 1, 0. The graph will go through the point 1 on e, negative 1. Sorry. And it will also go through the point e1. And so we get our standard log shape. It's just that the coordinates of the points are going to involve e. So ln x, or log base e of x. Transformations can be applied to the exponential and the log functions in the same way that they're applied to all our other exponentials and log functions. Okay, so let's think about sketching the graph. Sketch the graph of e to the negative x plus 3, showing all key features. Okay, so it is an exponential graph, base of e, that doesn't really matter. The negative here is going to reflect our graph in the y-axis, and plus 3 is going to move it up by 3. So we've got reflection in the y-axis. So that means our exponential graph shape is going to go this way, and we're going up by 3, which is going to change where our asymptote is. So we're going to have y equals 3 will be the asymptote. Thinking about the shape, it's going to go this way, so it's not going to have an x-intercept, so we just need to calculate the y-intercept. When we let x equal 0, e to the 0 plus 3, so that's going to be 1 plus 3, 1 plus 3, so the y-intercept is at 4. So again, being consistent about my scale, that means 4 needs to be about there. I'm also going to need another point on the graph, so you might, for example, look at when x equals negative 1. When x equals negative 1, y will be e to the negative 1, so it's e to the 1 plus 3, so it'll just be e plus 3. So we'll simply mark that point in. It's going to be negative 1, e plus 3. The coordinates of the point are the y coordinate is e plus 3. There's nothing more you can do to simplify that. That would be, given that e is about 2.718, that would be at 5.718. Okay? But that's an approximation, so to write it exactly, you would write it as e plus 3. Alright, let's think about example 2. Sketch the graph of y equals e to the negative 2 e to the x minus 1. The negative out the front is reflection in the x-axis. So my graph shape is going to be going this way. We've got a dilation by 2 from the x-axis, but that doesn't really change how we draw it. That'll come into our calculations of points, and we're moving down by 1. So we're going to have an asymptote at y equals negative 1, and the graph sits completely below that asymptote, so it's never going to cross the x-axis. Y equals negative 1, so we only need a y-intercept, not an x-intercept, but then we'll need another point. So the y-intercept, letting x equal 0, so it's negative 2 times e to the 0 minus 1, so that's negative 2 times 1, so negative 2 minus 1, so it's at minus 3. So if that's 1 there, 2, 3, so negative 3 will be about here. And we're going to have our graph going this way. Okay, let's mark another point. So perhaps when x equals 1, y will be equal to negative 2e minus 1. I'm just going to label that as that. Okay, so we're going to have 1, negative 2e minus 1. So in many ways it's easier. You don't need to evaluate it. You simply can just write negative 2e minus 1 is the y coordinate at that point. Okay, example 3. Sketch the graph of y equals log e of x minus 5. So that is a log graph, no reflections at all, so the shape is still going to be this log shape, and then we have gone to the right by 5, so that's going to move the asymptote. So y-axis over here, right by 5, let's sort of 1, 2, 3, 4, 5, put some other points out here, because we'll no doubt have a x-intercept somewhere out there. X equals 5, let's work out that x-intercept, so we need to let y equal 0, so 0 equals log base e of x minus 5, so we're going to need to change from a log equation to an exponential, that is e to the 0 equals x minus 5, so 1 equals x minus 5, and so x equals 6. Alright, so our x-intercept is going to be there. Oops, sorry, my touch screen caught on my hand. Alright, so alright, we're going to need another point, so we've got the point 6, 0, so you might look at when x is 7 or 8 or whatever you want, it doesn't really matter. Might go with when x equals 8. Something bigger than 5, obviously. Bigger than 6 would be better. So we're going to get y equals log e of 8 minus 5, so that's 3. You might write that as ln 3, just as a shorthand, so it's a bit neater. And so I'm going to mark the point 8 ln 3. If you'd subbed in 7, you would have had 7 ln 2, or 7 log base e of 2. You can write it out, it's fine. Alright, so there's our graph. Okay, number 4, sketch the graph of y equals ln of 3 minus x showing all key features. Okay, so a number of things here. We've got, this is log base e, just to be clear, and then also thinking about your transformations correctly, you want to factor out that negative, so it's this, so you've got your reflection in the y-axis and then right by 3. So reflection in the y-axis, so my shape is going to go this way, and then we are going to the right by 3. Okay, so our asymptote is going to move across to the right. Again, sometimes it's easier with these to think about domain. you know that 3 minus x has to be bigger than 0, and so 3 has to be bigger than x, which means x must be less than 3. So therefore your domain, your asymptote's going to be at 3, and your graph's going to go back here to the left. Okay, so we should be able to draw in our axes. We're going to have asymptote at x equals 3. We're going to go this way, so we're going to be crossing both the x and the y axes. So y-intercept is when x equals 0, so that's just going to be log e of 3. Okay, and your x-intercept, now remembering log base e is close to 3, so log base 3 of 3 is 1, so it's going to be not too far away from 1, that value, ln of 3. And then your x-intercept, you're going to let y equal 0. And again, easier to think about ln as being log base e. That's why I usually write it out, so I can think about this rearrangement. So I'm going to change it to an exponential. It's e to the 0 equals 3 minus x. Okay, so 1 equals 3 minus x. Taking away 3, negative 2 equals negative x. And so x equals 2. So again, thinking about your scale here, making sure that 2's in about the right place. It should be sort of 2/3 of the way to that asymptote. And then your y-intercept we decided was somewhere around about 1, but again I've got no other points marked on the y-axis, so I just need to draw in my shape and then label that at the right place. Okay, so this is the point 2, 0, and this is the point 0, ln of 3 or log base e of 3, however you choose to write it. Okay, all our index laws and log laws and methods for solving exponential equations and log equations still apply when we have expressions involving base e. So let's solve some equations for x. So if I've got e to the power of x minus 4 minus 6 equals 7, first thing I'm going to do is get the exponential part on its own. So I'm going to add 6 to both sides. So e to the x minus 4 equals 13. And then we're going to change it from an exponential equation into a log equation. So x minus 4 is equal to log base e of 13, or ln of 13. And then x is going to be equal to log base e of 13 plus 4. And so we're done. As I said, you could also write that as ln 13 plus 4. Both are perfectly correct. They're no different. Okay, part B, log base e of 4 on x is equal to negative 2. So again, let's free that 4 on x out of the log by changing it to an exponential. So 4 on x is going to be equal to e to the negative 2, which means 4 equals, well, let's do a couple of things here. So e to the negative 2 means 1 on e squared. So 4 equals x on e squared. And so x equals 4e squared. Okay, part C, again, we're looking at this addition and subtraction. Your index laws don't allow you to add indices together, okay, even if they've got the same base. So we're going to need to make a substitution here. So we're going to think about the fact that this is e to the x squared is e to the 2x minus 8 times e to the x plus 15. And so I'm going to let u or a or whatever letter you want to use be e to the x. So we get u squared minus 8u plus 15. Factors of positive 15 that add up to negative 8, negative 3 and negative 5. And so u equals 3 or u equals 5. And so therefore e to the x is equal to 3 or e to the x is equal to 5. We're going to need logs to solve both of those. So x is equal to log base e of 3 or x is equal to log base e of 5. And there is your two solutions to the equation. So sketching exponential graphs with the base of e, log graphs with the base of e, solving exponential and log equations involving base e. All the processes are the same, just introducing this idea of this new number called e, which is equal to about 2.718, so a little bit less than 3.